You all are warmly welcome to another session of the series of interviews, which is brought to you by the Department of Chemistry, University of Colombo. I am Janak Sampath, who is a fourth-year chemistry special undergraduate. In this series of interviews, we will be interviewing eminent scientists who have done a great job in the field of science. Especially in this series of interviews, we are going to explore some unseen dimensions for scientists. So for today's session, I will be interviewing Professor Bart Bartlett, who has currently excelled as a professor of chemistry in the Department of Chemistry, University of Michigan. Good morning, Professor Bart.
Good morning.
Thank you very much for accepting our request to engage in this interview, though you have a very busy schedule.
Yeah.
To begin with, would you mind telling us a little bit of yourself? I mean, about your family background, early education, and so on. Actually, how has your upbringing shaped you?
Yeah. Again, my name's Bart Bartlett. I'm at the University of Michigan. I originally am from St. Louis, Missouri. It's a medium-sized Midwest town here in the United States. And when I was growing up, neither of my parents had a science background, but they knew that it was very important, for me to get an education. So both of my parents, they met each other at their workplace. They worked in a steel manufacturing plant making the pipes that we use in heating systems. And so, they always aspired for me to get an education so that I could work with my brain and not work with my hands as they did. And so, and nothing wrong with that, but that was always their goal for their children. And so that really inspired me, their encouragement for me to do well in school. I remember them always telling me, as I was, in school, that they were proud of the work that I was doing, and, were very encouraging. And that was important because it showed me that, I could move beyond and do anything I wanted to do when I grew up, because I knew I had their support. My spark for science really began when I was in high school. I had a great high school chemistry teacher who got me connected, actually, with the Washington University. That's a university in St. Louis. Their School of Medicine had a young scientist program for high school students. So that was the first time I had done lab research in a genetics lab. And even though I'm now a chemist, it was that experience that introduced me to how scientists work together as a team to collaborate to solve problems. And so, my upbringing and sort of family background was important because, it gave me the encouragement to go out and to try new things that my parents hadn't experienced themselves, and they were completely supportive of that.
Professor, you have already answered partially to my next question,
Okay.
but I think it's necessary to add a little bit more to that.
Okay.
How did you become interested in science? I mean, especially in chemistry, was there a particular turning point in your life that stimulated to become as a chemist?
Yeah, I point back to high school, and the chemistry teacher that I had there. So my two favorite subjects in high school were chemistry and geometry, which is why I love doing solid state chemistry, thinking about the geometry of solid compounds. And so, that's where, sort of my interest in chemistry, as well as, I was good at it. So I liked it for that reason. And, what I appreciated, I always enjoyed science and math classes up until that point. I think I got more excited about chemistry than I did about math, just because I liked the lab aspect of, doing the experiments that we did in our high school lab. And that's really what got me excited, and that spurred me on. Then when I started my undergraduate studies, I ended up going to Washington University in St. Louis. It was really important for me to get involved in undergraduate research, because I knew, just how important doing the experiments were, working with other people, to make progress on ideas.
Yeah. Professor, I was able to find that you have a very nice research group. So what do you think about teamwork? Is teamwork important for scientists to achieve their goals?
It's vital. It's crucial for teamwork. The idea that you can do top-notch science in the 21st century all by yourself, with this idea of, kind of the mad scientist. I don't have any hair anymore, but, with a guy with big crazy hair and boiling solutions in a basement or something like that, the mad scientist, that's totally not how this works. It really takes a community of scholars who think about different problems, who develop different expertise in order to really refine their ideas. And I see that a lot in my research group. Everyone in their PhD research has their own independent project. They've got to make their own contributions to science. But it's crucial that they teach each other, that they learn from each other, that they communicate with each other, not only to teach each other how to do experiments, just how to think about science as well. And that's really a critical point. I know often I found when I was in grad school, and I see it in my own students and undergraduates as well, this is not just for the graduate students, when you get stuck on a problem, it really takes an outside perspective, someone else to hear, well, what have you tried? Have you thought about this, to start to make those breakthroughs and to make advances?
Yeah. In addition to teamwork, what are the other traits that a scientist should possess in order to become successful?
I think outside of, being able to work together as a team, I think individually, just having a genuine curiosity, keeping your eyes open. A lot of times experiments don't work as you think they will in the laboratory. And, it's really important to not see that as failure, but to recognize that there are still things to learn from every experiment that you do if you've thought it out well. So being perceptive and genuinely curious, I think, are crucial traits in order to be successful. And then, the other keys are then knowing what other people have done. So you got to read a lot. People ask, well, how do you come up with new creative ideas? And there are very few of these moments where you just have some independently thought up new idea. In order to generate new ideas, you really have to know what other people have tried and to sort of build upon that. And so reading a lot and being curious so that when you're onto something really new is a really important trait.
Yeah. Generally, scientists have to experience so many failures during their research work. I think there may be time periods where nothing works actually. My question is, what do you think about those failures, and how do you deal with them?
Yeah, so here in the United States, my favorite sport is the sport of baseball. And in baseball, all you have to know about the game itself is that, if you go and you can hit the ball, 3 out of 10 times, I mean, that's a superstar career in baseball. In chemistry, if you do experiments in the lab and 1 out of every 10 experiments work as you think they should, that's a superstar career in chemistry. So what do you do with the other 9 times out of 10 that things don't work? I think part of being able to persevere, like I was saying a moment ago, is one, to recognize, well, what specific variables do I need to change up as I do experiments, so I can recognize the difference between things I'm doing wrong because I'm not thinking about it correctly versus, things that here I'm on the right track, but I just need to collect a little bit more data. And this, again, is where talking to other people is really important, and having a good relationship with your research mentors, people who've done this, not that we claim to be more expert at it by virtue of being smarter, but we've just done it a little bit longer to recognize and to redirect projects. And so it's why it's so important, going back to, one of the earlier questions about teamwork, it's why it's so important is that, when you get kind of stuck in a rut because 9 out of every 10 experiments isn't working, trying to pull yourself out of that all alone is really tough. And I'd argue it's a really bad idea. And so communicating your science to other people, recognizing where others can help, getting a perspective from someone who works in a slightly different area, who may understand the experiments, but will ask deeper questions about, well, what are you really trying to do? Is there a better way to answer that question, or a better question that we could ask based on the data that you have? And so, just working with other people, I won't say that it's always easy to have experiments not work in the lab. I mean, you should take it a little bit personally. if you care about what you're doing, but not to let that define who you are as a person. I think one of the things that we're much better at now than even 20 years ago or so when I was starting graduate school is recognizing that how things are going in the lab is not a reflection on who you are as a human being. And so, and to work together to solve these problems.
Professor, could you please give us a brief explanation about the types of research work that you are currently focusing on?
Yeah, so we have two major problems that we think about in my lab. And again, everyone's got a slightly different project within that they're working on. But the two major areas or questions that we ask are, on the one hand, for solar energy conversion, basically, how does the structure of the electrode and its chemical composition at the surface in particular influence the rate at which it can carry out catalytic electron transfer reactions? And so, we generate electrodes of different sizes and shapes, morphologies, the fancy word we use for that, electrodes with different chemical composition at their surface, in particular looking at how they catalyze the oxygen evolution reaction, so taking water and turning it into oxygen and hydrogen, or as we're now starting to do, to apply that same sort of science to taking chloride, which is a main component in salt water, seawater, and oxidizing that to chlorine, which is useful for a lot of organic transformations. Yeah. But we're really focused on the fundamental mechanisms of electron transfer at the electrode-electrolyte interface. So that's one real project in the group. The other project looks at the deposition of metals, specifically magnesium metal, for multivalent battery chemistry. So we're all familiar nowadays with lithium-ion batteries. We use them in our portable electronics. But a key question is, how do we go beyond the one electron chemistry of lithium-ion to doing multi-electron chemistry for, say, magnesium 2+, 2 electrons, and looking at the mechanisms by which I can take solvated magnesium ions in organic solution and deposit them as magnesium metal for the negative electrode of that battery.
According to my opinion, scientists always try to explore the unseen aspects of the nature, or to invent something which is going to be beneficial for the environment as well as human beings. So how can your work be helpful to the environment and to the human beings?
Yeah, I think if we are successful in some of the aims that we have, thinking about these problems in energy conversion and energy storage, we need energy to power our lives, our devices, our homes, our businesses. So, figuring out ways that we can better utilize energy, to grow our economy, to increase our well-being as humans, that's a key aspect of what we do. We also recognize that how we currently get energy, largely, from combusting fossil fuels in one way or another, in order to get energy out is bad for the environment. So anthropogenic, that is human-made carbon emissions, is a huge problem that, despite what some folks may think, has demonstrated detrimental impact on the environment. And so if we can find ways to use solar energy to convert photons to make electricity, or to make fuels or commodity chemicals, and energy storage technologies in the form of batteries, again, that don't liberate lots of carbon dioxide, we hope to accomplish both of those goals, to make our lives better, both now and for our children.
Yeah, it's clear that you have focused your attention on greener production protocols of renewable fuels, where, for an example, we can use photocatalysts for full-forming reactions such as water splitting.
Yeah.
Here, I would like to be specific on photocatalysis because I am also interested in that. So my question is, if we discover a novel photocatalyst, what are the characters that our compound should possess in order to become superior over already existing ones?
Yeah, so that's a good question. It's one that I think about a little bit, but not a lot. And so, and here's why. So, in terms of developing a photocatalyst, I'll use that as an example. We know what the right sort of characteristics are. We need to absorb as much light as we possibly can. turn that light into separated charge carriers that can do useful chemical transformations. And the more efficient that process is before the electrons do other things within the material or at the surface, we want that to happen. Then we want the chemical reactions to go as fast as they possibly can, so being a good chemical catalyst. So we know all the characteristics, and we know something, and the community has taught us, and I hope I'm teaching the community something about, well, which particular materials in terms of their electronic structure, their light absorption properties, optimize each of those functions. But here's the hard part. So I'm a basic scientist, and I'm unapologetic in being a basic scientist. I know that even if we make good inroads in understanding, how to improve one of those features for making a better catalyst, it'll be good for today, maybe tomorrow, and maybe next week. There are lots of talented scientists, creative people in the world working on these problems. So, I never set my sights on making what I think is, quote unquote, the best, highest performing system, because you're only going to be highest performing until someone else comes along, and improves that, which is a good thing. But what's really important then is not so much that we're trying to make the best catalyst or photocatalyst, but that every experiment we're doing, all the papers we write, we're teaching everyone something about what we've learned about the photophysics, about the photochemistry, about the catalysis, so that, as we continue to make progress, even if we're not making the best, we're always learning something new, so that whether it's our group or someone else's group, can continue to make improvements and translate the technology from the benchtop to the marketplace. That's what my engineering colleagues are expert at, going from benchtop to market. And occasionally scientists do this with great success, but I don't wake up every morning thinking, how am I going to make the best system? Because if I did that, you'd never reach the goal, right? So for me, it's about learning the fundamental science.
Yeah. My next question is related to the future of chemistry. Which areas would be the future of chemistry? What do you think about that, and why do you think so?
Yeah, I think the future of chemistry and many disciplines within science, for that matter, are really going to be where we take sort of the traditional fields. If you go and look at the names of textbooks, behind me here, and start to bring people together who work at the interfaces of those fields. So, for example, in the research that I do, I trained as an inorganic chemist, and what that means is that I think deeply about how structure, composition of matter, particularly metal oxide materials, metal-based materials, influence then how they react towards these reactions of oxygen evolution or metal electrode deposition. But in order for me to do that really well, nowadays, we also need to combine with that folks who know things about, for example, big data, how to take massive amounts of data from all the experiments that we're able to do now, and so that, again, we can start to bend that data together more quickly. It's great for me to come up with hypothesis-driven science, but it's also important just to try lots of things. And we're able to do that, and it's tough then to reason through all of the data that we're able to collect in, incremental changes in composition and structure and building multiple phases, lots of space that we can explore. And so we need new methods there. And so having big data and theory that can help. And, these are not areas that I train. I mean, there's not time in my life to train and to be expert in all of these different areas. And I also think about the ways that we're now able to interrogate structure and composition, using synchrotron radiation and, really ultra-fast time scales to look at multiple length and time scales for all the processes that I talked about a moment ago, for example, in making a photocatalyst. And so, having expertise across multiple disciplines is the way that science is really advancing nowadays. And so, doing collaborative work, and this goes back to now, not just teamwork within a lab, but how to well collaborate between labs. I think that's where the future of chemistry is going. I think that's where the future of lots of fields, so the interfaces between chemistry and engineering, biology and medicine, physics and engineering, these are all the ways that science and the varying disciplines are going to develop as we continue here in the 21st century.
Yeah. Professor, you are mentoring and teaching young students who are still building up their lives. On your point of view, how important is it to be a good role model?
Yeah, I take that very seriously. I got into what I was doing for a living. You know, what solidified me wanting to really be a professor is that the professors that I work with as an undergraduate, as a graduate student, as a postdoc, I really appreciated that they were all very transparent about what this job requires. I like 90% of my job. You know, I really enjoy teaching students. I enjoy working with the students in my lab. Some of the, committee meetings and service work I could do without, but, it's a necessary part of the job. But I appreciated that they showed me that those are the things that are required to do it, and they modeled that for me. And in turn, it's really important that I model that for my students so that there's no surprises. I want to show them what this career is like. I think one of the things we've done a lot better since I've started at the University of Michigan is, I'm a professor, and a lot of my students, some of them will want to be professors, but a lot of them will want to join chemical industry and have other careers where having a scientific background is crucial. And I'm grateful that we brought back a lot of our alumni who have varying careers so that they too can be transparent and show students, well, here's what it's like to work in chemical industry. Here's what it's like to work in law or to teach, exclusively for a living. And so, yeah, modeling what we do is very important for then attracting new great talent to want to do it. And so I take that extraordinarily seriously.
What is the advice that you would like to give to a young person who is going to enter this exciting field of research?
Yeah, I think the main things are, a lot of the topics we've hit on. So one, keep your eyes open, use all of your senses, not just what you can see. But when you're in the lab, be perceptive about what's going on. I think understand that science really is collaborative, that this is a people business. A lot of folks, particularly, young school kids, they get this idea that, scientists, they're pretty antisocial, they're nerds, they don't have any fun. And that could be farthest from the truth. I think, it's very fun. It's very collaborative. It's a very social existence. And so, I think for those reasons, it's really fun. There's a lot of camaraderie that's built. Some of my best friends in life now are people that I met when I was in college doing, undergraduate chemistry, my friends from grad school. So that's important. To stay genuinely curious, to always be asking questions about, well, what's happening in the world around me? To have that want, to really want to understand what's going on and to probe that deeply. I think that's important. And, the last piece of advice is just, as you're in your studies, preparing for career, whether it's in science or whatever it may be, to enjoy it, to have fun, to take advantage of the people that you're around, whether it be your teachers, your professors, to take full advantage of those opportunities to have and own a transformative education.
My next question is going to be a common one. Professor, how do you spend your free time? I mean, outside the office or the lab, what is your favorite activity?
Yeah, so that's a great question. My answer has changed a lot over the years. When I was in graduate school, my favorite things to do were to sing karaoke and play softball. I played a lot of softball. My favorite sport's baseball. I couldn't make it as a baseball player, but I like playing, recreational softball, and that was fun. Nowadays, I still play in a softball league, and I enjoy cooking a lot. Most of my time, though, these days is spent. I have a 9-month-old son, so I spend a lot of time just being his dad and enjoying watching him learn to. He's starting to learn to walk, so that's exciting. We also have my wife and I 2 big dogs that we love to run around and play with. So my family and enjoying them and being with my wife and kid and my dogs, that's what occupies most of my free time now. But with them, I still fit in my love of softball, and they enjoy the fact that I like cooking they take advantage of that.
Normally, professors have very busy schedules. That's something that we all know. How do you manage your time with your day-to-day activities?
It's hard sometimes, particularly now. I would say that's even harder than ever, because I'm working remotely during the global pandemic here. So my students
Yeah.
are in the lab, still making discoveries. We're able to socially distance when they're in the lab. They wear masks so that it's safe. But to keep the number of people in the chemistry building, down, they ask the faculty, because I don't go in the lab anymore and do experiments with my own two hands. They ask us to work remotely, and so. Managing time while, again, caring for a 9-month-old son, and still, interacting with my students and colleagues. Yeah, it's hard, but what I ultimately do is I try to set priorities, and I try to prioritize, I guess my family first, my research and teaching second, and then any of the other aspects of the job, as is necessary. And I also, I guess, two things that I think are important, maybe not necessarily for being a professor right now, but even for the students, is I try to set aside some time. I wish I could say it was every day. It used to be every day, but set aside some scheduled time just to read, so that I'm keeping up with what's going on in the literature in my field, so I know what's going on. And then I also just try to keep some or to schedule some time just to think and reflect on what my students are working on, who needs help in their project, where is this going next, because I find if I don't set aside time to do that, other things immediately fill in. It's like a vacuum. It gets filled in very quickly with whatever can occupy that space. So to set aside and to dedicate some time for thinking and reflecting.
As we all know, scientists have to come up with creative and novel ideas, from which they can plan their way forward in doing research projects. As a scientist, when do you get your most creative ideas? I mean, while thinking about a new idea, working, playing, or doing anything else?
Yeah, it comes from all of those things. I mean, where I get ideas, sometimes it's while I'm just, in thought, while I'm cooking or doing something else or exercising. Um, a lot of times it happens as I'm reading papers. I'll get ideas that are sparked from that. So yeah, I keep a file on my computer and a paper notebook around so that I can jot down ideas as they come. But yeah, they come all times of the day and night, sort of anywhere. And that's sort of the fun part about the creative process, and the limitation with the answer I just gave in the last question. Even though I do set aside time to think, it's all my ideas don't come within that window, right? But I think it is important to continually to be reading and reflecting, because you have to have something for that idea to come from. And so as much as I can know what other people are doing and what we're currently working on, I think that helps. But yeah, the ideas they come at unforeseen times. And one of the best ideas I had, I used to ride the public bus from the house I used to live in to campus. And yeah, I used to have a lot of good ideas just sort of sitting. It was about a 20-minute bus ride, and yeah, I would just think about all kinds of things. Sometimes I would start thinking about baseball and other stuff, and then my mind wanders to science and an idea comes. I mean, it's just all over the place.
Yeah, this is my last question, which is going to be about this interview. What do you think about this interview? Could you please give us a comment about this conversation? Here, your insight would be much appreciated.
Yeah, I appreciate the opportunity to talk about all these various aspects of what it's like to do science, in a collaborative research environment. So I think The length of this interview has been outstanding. We hit on all the questions. I think you sent something. It was on the order of 12 questions or so that we've talked through here. When I first read it, I was like, man, this is a lot of questions. But as we started to unpack it, I realized there was a lot of opportunity to hit on several themes that overlap in a few of the questions, which I think is always good in an interview. And knowing the audience as we began discussing here today, putting this together for other students just to see what it's like, that's also helpful. It helps to tailor then, how I respond to the questions, and it's helped me to reflect back on what did I most want to know when I was an undergraduate student, when I was a graduate student, looking to the next phase. And so, as much as what I've shared today is, I hope, helpful to others and exciting. I hope it helps demystify what this job is about. So that's the point here. And as we post this and as it becomes live, of course, if people have questions, feel free to reach out. An interview is only as good as the ability to talk to other people. And so I've greatly enjoyed talking about my experience here today. But if there's other things that anyone wants to know that I haven't quite said here, send me an email.
Thank you so much, Professor Bart, for your comment. Again, thank you very much for allocating your valuable time for this interview. Professor, your participation is highly appreciated. You shared so many information with us. Actually, 20 of them showed us a variety of unseen aspects of the life of a professor, of a scientist. Definitely, they will encourage us to do well in science and to become as a successful scientist. So now we have reached the end of the program. Now I am going to wrap things up. Today, we interviewed Professor Bart Bartlett from the Department of Chemistry, University of Michigan. I believe that you gained a huge inspiration through this program to grow as a scientist with proper qualities. So thank you very much for joining with us today. Have a great day.